Okay, today we are going to talk about energy efficient cooperative sensing scheduling for cognitive radio networks, and my name is Salim Eryigit. I am a PhD student from this university, and this is actually a part of my PhD thesis. So these are the topics that we are going to discuss today. After a brief introduction, we are going to discuss the system model upon which we built our optimization model and then solution methodology. After building the model, we are going to turn our attention to the optimization model by defining our decision variables and then applying some solution procedure. And then we are going to try some heuristic approaches which have low running complexity, but of course a worse objective value. After performance evaluation, we are going to reach some conclusion, and then we are going to discuss the same problem with switching cost. What is the switching cost? We'll see that in detail later on. So until 4 or 5 years ago, energy efficiency is considered to be an issue just for wireless sensor networks, you know, small tiny sensors that are distributed over a field with limited batteries, and the problem was to maximize the lifetime of these sensor networks in order to be cost effective. However, nowadays energy efficiency is a major problem, which means it is also an active research area for all types of networks, and the reasons for this can be attributed to these three factors. From the operator point of view, the energy cost of operating a network is approximately 30% of the operating expenses. So it's a huge number. From the global point of view, as the data traffic increases exponentially thanks to the internet and social media, so do our energy consumption and then our carbon emission. Okay. From the environmental point of view. And then from the user point of view, since you access internet from mobile devices every now and then as you watch especially video, your battery drains more quickly, and with these smartphones you must, I guess, charge them every day and maybe twice a day. So we are going to focus on energy efficiency from the point of view of sensing scheduling in a cognitive radio network. Sensing scheduling can be roughly defined as deciding which channels to sense and by which users to sense those channels, and then maybe some other operational parameters for the sensing procedure, for instance sensing threshold or maybe the duration of the sensing. And the actual problem that we are going to focus on in this presentation is how to perform sensing with minimum energy consumption and satisfactory performance in a cooperative manner. In literature, most of the people focus on just maximizing the detection probability. Okay, it is another performance criteria, but if you maximize it, you also increase your energy consumption. So in this presentation, we are focusing on satisfactory performance, okay, that is going to satisfy the operator and the mobile users with minimum energy consumption. Okay, let's talk about the model that we are going to discuss. We assume an infrastructure cognitive radio network with a base station. And we have n secondary users and m channels, and then the number of secondary users is very large compared to the number of channels. We assume that all channels should be sensed. Since we assume that the number of secondary users is very large compared to the number of channels, we assume that it is possible. If this is not the case, maybe for some specific applications, we need some elimination procedure to eliminate some channels from this set such that all channels can be sensed. And we assume a periodic sensing and quiet sensing period. You all know what quiet sensing means, right? All secondary users stay silent and then they sense the channel or channels to detect the primary users. And we assume hard decisions. You know, hard decision was a 1-bit decision. 0 means no primary user and 1 means there is a primary user. And then finally, we are working in a cooperative environment. We fuse the individual decisions using the OR rule, or maybe you have heard it as OR logic. You know, OR logic was, okay, let's say 3 users sense a channel, and then if just one of them says there is a primary user, and then the result was 1. Okay, for OR rule. For AND rule, in order to have a result of 1, all secondary users should decide that there is a primary user. Okay, and then we have majority rule, and then we have K of n general counting rule, etc., etc. In this presentation, we are just focusing on the OR rule. So this is our frame structure. At the beginning of the frame, we have a quiet sensing period which is of length Ts. And in this sensing period, a secondary user senses some channels. And then after the sensing procedure, the secondary users transmit their sensing results to the base station in this reporting period, which is of length Trep. And after these 2 periods, the transmission period begins, and if we say T is the total frame duration, its length is T minus Ts minus Trep. Now remember, N was the secondary user index and M is the channel index. So if secondary user N senses channel M, tau Mn denotes the sensing time for secondary user M in order to sense channel M. Okay, now we have this formula which seems a little bit complicated, but for our purposes for this class, we will try to keep as simple as possible. It says that, okay, let us begin on the basic. This is the Q function, and Q function, you know, let's say this is the standard normal distribution or Gaussian distribution, and Q function is the what we call the tail probability of the standard Gaussian curve. So it has a graphic like something like this. Okay, this is the Q function. So this formula says that the probability of detection for secondary user N for channel M is related to the false alarm probability for secondary user N channel M, sensing duration. This is Fs is called the sampling frequency, which is of type Hertz. Its unit is Hertz, and gamma is the SNR value. Okay. So, you know, if we observe this formula, increasing the sensing duration or sampling frequency or SNR value decreases the inside of this function, and then it actually increases the detection probability. Okay. Also, I guess you all know this, also increasing the false alarm probability also increases the detection probability. Okay.
So detection may be a false detection and a true detection. right?
You know, this is just a probability. Let's say it is 0.9. So with 0.9 probability, it is a true detection, and with 0.1 probability, it is a misdetection.
So this is the total of the two things that you say.
Two things.
Try to sense the medium for a primary user,
Okay.
and this formula says that.
This formula says that the longer you listen, the higher the probability of detection. Okay. And the larger the number of samples you take, again, the higher the probability of detection.
Okay,
And then
but I didn't get the false alarm probability effect of this detection.
Okay, then let's give a trivial example for that. For instance, assume the extreme case that regardless of any sensing, you always say that there is a primary user.
Okay.
And then in this such a trivial scheme, your probability of detection is 1, because you always say that there is a primary user. But your false alarm probability is also 1. Okay, because you don't perform any sensing, you always say that there is a primary user. So increasing false alarm probability also increases the detection probability.
Okay,
Okay, we have a theorem here, but we will just skip it. It just says that, as I already said before, the detection probability is an increasing function of the sensing duration. It makes sense, right? The longer you sense, the higher your probability of detection. And now we have another lemma. It says that the detection probability is a concave function of the sensing duration if the detection probability is larger than 0.5. Now this condition is of practical value, since in a practical application you always want a detection probability larger than 0.5, otherwise it would be meaningless, right? So we can say that for practical applications, the detection probability is a concave function of sensing duration. If you don't remember what a concave function is, a concave function is a V-shaped function. You know, this is a concave function. And the reverse of this is what we call a convex function. The simplest example for a convex function is x squared, and for a concave function, minus x squared is the most simple examples. Okay, in mathematical terms, a convex function is a function whose second derivative is always positive, and this is just the reverse, whose second derivative is always negative. Just for mathematical clarity.
So if Tmn means the sensing time,
Yes.
value increases, this means the PD decreases, right?
No.
According to this function.
Okay, there are, this is just an example of a concave function. There are lot, yes, for instance, you know, this is also another concave function.
Which always increases.
Yes. In the previous slide, we already explained that the detection probability is an increasing function of tau. And then if this is a concave function, then 1 minus this becomes a convex function. It's simple. Now we said that we are going to use some cooperative detection. Okay, then let's try to write the cooperative detection probability. If we let Sm be the set of secondary users that are going to sense channel M, and QMD denote the cooperative detection probability for channel M, if we use OR rule for fusion, the cooperative detection probability is given by 1 minus the multiplication of, this is misdetection probability, multiplication of misdetection probabilities. Okay, so this part is what? The probability of misdetection, because when you use OR rule, in order to misdetect, all secondary users should misdetect, right? So this is the probability of misdetection, and 1 minus this is probability of detection. So what we do is we just plug this formula with the Q function and the other variables instead of probability of detection here. Okay, any questions up to this point? All right, let's move on. Now this is also another theorem which and its proof is a little bit complicated, which we will not discuss here, but it says that the detection probability is an increasing function of tau, which is, I guess, intuitive. Moreover, it is also concave if the condition in one, which was this condition, and which was satisfied if probability of detection is greater than 0.5, if that condition is satisfied for all secondary users that sense channel M, then it is also concave, the cooperative detection probability. Now, what we contribute in our work is that in the literature, people always assume that a secondary user senses just a single channel in the sensing duration, and then they switch to an idling mode or transmission mode, whatever. In our work, we assume that the secondary users can sense multiple channels as long as they finish sensing in the dedicated quiet sensing period. Okay. And usually in the literature, people assume that the link conditions for a channel are the same among all secondary users, but which is actually not the case due to some propagation characteristics and geographical conditions. So we account for the heterogeneity of the secondary user link conditions. And by heterogeneity, we mean that, for instance, I am here, and let's say my SNR for channel 1 is different from, let's say, the friend at the back, because he is just behind the wall. And we decide on which secondary users should sense a channel, and if they should sense a channel, which channel they should sense, and then we also decide on the sensing duration for a secondary user. Now, I have already told you that our main goal is to achieve satisfactory sensing performance with minimum energy consumption. So, how do we consume energy while we perform sensing? In this part, we have two components for the energy consumption. One is the actual energy that is spent for performing the sensing task. And let's say that if PS is the sensing power, then tau mn is the sensing duration, PS tau m times tau mn is the sensing energy that is used by secondary user n for sensing channel m. If we sum this for all channels and for all users, okay, this is the sensing energy that is used for sensing the task. And we have also another leg of energy consumption, which is usually neglected, and it is reporting energy. And reporting energy means that when you sense a channel, you need to transmit your sensing results to the base station. So you need to transmit a packet, which also consumes energy. And let's say that the reporting energy is given by EREP, and its formula is SREP means the set of secondary users that sense any channel, so that they should sense a reporting packet to the base station. If we sum the energy consumptions over all the secondary users that need to send the packet, we get the reporting energy. Now, in a typical optimization, we should define the decision variables for the optimization problem. And we already discussed what tau mn means. So I'm going to skip that one. We have also another decision variable, xmn, and it assumes the value of 1 if some condition is satisfied and value of 0 if it's not satisfied. This means otherwise. These type of variables are called binary variables. They just assume either of the two values. So xmn takes the value of 1 if secondary user n senses channel m, and it assumes the value of 0 otherwise. And we also have another variable yn, and it says that it assumes the value of 1 if secondary user n transmits sensing results to the base station and 0 otherwise. This also means that since it transmits sensing results to the base station, it also means that secondary user n has sensed one or more channels, okay? Because it needs to send some sensing results. Okay, we have some other constraints which is typical again in an optimization model. Let's start with them. If secondary user n senses a channel m, then we require that the detection probability should be greater than 0.5, and this was the convexity, or maybe you remember as the concavity condition for the detection probability. Okay, it makes sense because as we have discussed before, a detection value less than 0.5 is meaningless. So based on the formula, we calculate a minimum sensing duration, tau minmn, and it is given by this expression. It's not very important. It just says that if you need to sense a channel, your sensing duration should be at least this long. And in order to encourage cooperation, we say that if we sense a channel, and since we sense all channels, a channel should be sensed by at least delta min number of secondary users. So in our simulations, we usually take delta min as 3, so we say that a channel should be sensed by at least 3 secondary users. And then if we assume the false alarm probability is the same over all users and channels, then this is the cooperative false alarm probability, and its formula is very simple to the detection probability. This is, again, it was the misdetection probability here, and in this case this is no false alarm probability, and if we subtract it from 1, it is the false alarm probability. And by using this formula, and since you need to have a false alarm, cooperative false alarm probability less than some threshold, and if you use that formula, assuming all false alarm probabilities are the same across the network, you also calculate a delta max value. And remember, delta min was the minimum number of users to sense a channel, and delta max becomes the maximum number of users to sense a channel. Okay, so you need to have some number between delta min and delta max. This formula is not very important for our purposes. And we have another constraint that states that the total sensing time of a secondary user should be less than the quiet sensing period. Okay, now this is actually the mathematical model. We are trying to minimize the energy consumption, which consists of the sensing energy and then the reporting energy. Remember, yn was defined as it takes the value of 1 if secondary user n needs to transmit some packet, otherwise it is 0. Okay. So let's observe our constraints, and let's recall how to read a mathematical constraint. Okay, let's start with this one. It says that for all m and for all n, so it means for any channel and for any secondary user. Okay. The sensing duration should be greater than or equal to the minimum sensing duration multiplied by xmn. Remember, xmn takes the value of 1 when secondary user n census channel M. So we have two possible cases. If xmn equals 1, then this constraint will assume this form. So the sensing duration will be greater than or equal to the minimum sensing duration. But if this is 0, this expression becomes 0, right? So this can be anything greater than 0. But due to the objective function, since objective function tries to minimize tau mn values, it takes the value 0. Okay? Okay, let's move on to the second constraint. It says that for all n, that means for a secondary user n, for each secondary user n, the total time dedicated to sensing all channels, okay, should be less than or equal to the length of the sensing period times yn. Remember, yn means yn was 1 if secondary user n senses anything. So if yn is 1, this expression becomes this. Okay, so the total dedicated sensing time is less than the required sensing period. If yn is 0, this thing is 0. So since these are non-negative things, they all need to be 0. Okay. And let's move on to this one. For any channel M, or we can say for each channel M, the sum from n equals 1 to big capital N. So it means that the number of secondary users that sense channel M. Right? Is it clear? Okay. Then the number of secondary users that sense channel M should be greater than or equal to the minimum number of cooperating users. And this is very similar to this one. The number of secondary users that sense channel M, any channel M, should be less than or equal to the maximum number of cooperating users. And we have that this constraint actually links xmn and yn, because for a secondary user n, we want yn to be 1 if any of the xmn values is 1. Okay, so let's say that we have secondary user 1 that senses no channels, then we want y1 to be 0. But let's say if we have secondary user 2 that senses, let's say, channels 1 and 5, we want y2 to be 1. And let's say we have another secondary user 3 that senses 1, 8 and 11, and we want y3 again 1. So this constraint actually forces yn to be 1 if any of these xmn values related to the nth secondary user is 1. Okay. Remember, capital M was the number of channels. And finally, we have the detection probability constraint, which says that for any channel M, the cooperative detection probability should be greater than the threshold value for cooperative detection. And these two constraints just merely specify the types of the variables. Tau mn variables are continuous and non-negative, and xmn and yn variables are binary. And you know, this, in order to simplify this thing, I just said cooperative detection probability for channel M, but actually when you look at this, it looks very simple. It's just linear constraints, but actually this is not that simple. It's a nonlinear expression, and which is a little complicated, and we also included, remember, this was the previous formula. Now we have also incorporated the xmn value into this, which becomes a mixed integer and nonlinear expression, and the problem also becomes a mixed integer nonlinear problem. Okay, and which is of the hardest type of optimization problems. Now we apply a solution procedure that is defined as outer linearization or maybe outer approximation regarding the sources that you look upon. In this type of solution procedure, you know, other than this m constraints, the remaining constraints are all linear. So in an optimization point of view, from an optimization point of view, we love linear constraints because they are simpler, they are nice and easier to solve using commercial software. But this constraint complicates the problem. So the outer linearization procedure tells us that you just ignore the complicating constraints, and then after ignoring the complicating constraint, we solve the remaining mixed integer linear program to obtain an initial solution. Okay. So what we do is we ignore this constraint. Actually, this is m constraints, not just a single one, and solve the problem. And then we look upon the solution, and if the solution satisfies all the ignored constraints, then it is optimal. Okay. But usually that is not the case. Then we perform some linearization procedure, which I am going to describe a little bit, not to complicate things for you. And this thing works because due to our proof, once the XMN values are fixed, this constraint becomes a convex constraint. So it is bound to terminate. If it wasn't the case, that procedure should go on, may go on forever. The convexity of the detection probability, cooperative detection probability, guarantees finite convergence time. Okay. How does this thing actually work? Let's say, assume that we have a convex constraint like this. Okay, this is just not our problem specific thing, but just to give you an idea. Also, remember, you also have other constraints. I'm not drawing them on the board, but you also have another constraints. Now you solve the problem, and let's say this is your feasible region. Okay. You solve the problem and you obtain a solution. Let's say you obtain this solution. You see that this solution, remember, we ignored this constraint and solved the problem, and let's say we obtained this solution. This solution actually is not feasible. What we do is we linearize this curve by using its gradient and the solution we have found. Actually, what we do is we add a linear cut, a tangent at this point as a constraint, as a new constraint to our problem. Okay, so let's say that this is our new constraint. Then we again solve the problem. Let's say that this time we obtain this solution. And also it is not a feasible solution. Then we add another cut at this point. What we do is, since this is a convex function, actually we are approximating it with linear lines, which are actually the underestimators for this function. Okay, just to give you an idea. Okay, let's move on to another topic. Now assume that in the previous part we were trying to minimize the energy consumption. Another objective can be to maximize transmission time. And if we assume that the length of the frame, remember we have a frame and we have the sensing period, we have the reporting period, and we have the transmission period. If we assume that the total length of the frame is fixed, okay, and then the length of the reporting period is also fixed, in order to maximize transmission period, we should minimize the sensing period, right? So we have more time for transmission. And how can we calculate the length of the sensing period? It is actually among all secondary users, the maximum of the total time dedicated to sensing. So let's say the secondary user 1, let's say dedicates 30 milliseconds for sensing, the secondary user 2 dedicates 40 milliseconds, and then let's say secondary user 3 dedicates 25 milliseconds, then my sensing period should be the maximum of these values. It should be 40 milliseconds, right? So what we do is we need to minimize the maximum of total sensing times for all secondary users. The constraints are the same with our previous model. And then we again apply the same procedure that I've just described in order to solve it. Now, these two methods are exact methods to find optimal solution, and in practical applications, and since you use other commercial software, exact methods are slow to execute, okay? They take long time. So, we also implemented some heuristics. And in case you don't know, a heuristic means that it executes in polynomial time, and it doesn't guarantee optimality, but generally it gives good performance. Okay, it finds a suboptimal solution, but the critical point is that it executes in polynomial time. This time, for our heuristics, we fixed the detection probabilities for all secondary users and channels, and then we say that in the previous models, the number of sensing users for a channel is between delta min and delta max, but to keep it simple for our heuristics, we say that a channel should be sensed by exactly delta min number of secondary users. Let's just skip this one, it's not that important. We have two heuristics, and they are both greedy heuristics, and greedy means that they make the assignments greedily. They don't care about the feature, they don't care about the remaining assignments. Okay, this is a pseudocode, but we will not go into the detail of the pseudocode. Let's say that what it does is this. Initially, for all secondary users, the remaining time is equal to the quiet sensing period. And then, for a channel, we pick a channel from the channel set, and we try to assign the secondary user with the best SNR value to that for sensing that channel. And we calculate the required sensing time to achieve a detection probability, a given detection probability. If that sensing time, if the secondary user n has greater sensing time than the required value, then you assign that secondary user for sensing that channel. Otherwise, you move on to the next secondary user. The critical point is that you always try to assign the secondary user with the best SNR values for sensing that channel. Since the best SNR value also implies less energy, right? Now this is for a greedy algorithm for minimizing sensing energy, and then we have another heuristics. It is called reporting energy minimization heuristic. The logic is the same. Again, it tries to assign the secondary user with the best SNR value for sensing a channel, but this time it separates the secondary users into two sets. Let's say that we have a secondary user set, SU. We have a set of secondary users that are reporting, which means that they are already assigned a channel. And then non-reporting. Okay, what this heuristic does is it prioritizes the reporting secondary users, and the logic behind is that since I am already sending a packet to the base station, since I am sensing something, if I sense another channel, the network in total can save from the reporting energy, because regardless of the number of channels I sense, I only sent one packet, okay, to the base station. Of course, if there aren't any suitable secondary users in this set, then we go and look into this set. Okay, but this set has the priority. And these are the parameters for our simulations. We have a network with 40 channels, and the number of secondary users change between 160 and 240. The sampling frequency is something like 10 kilohertz or 1 kilohertz. And we assign the SNR values exponentially random with some the mean of the exponential distribution is something between minus 10 decibel and 5 decibel. And we say that a channel should be sensed by at least 3 users. We assume that the false alarm probability is 0.01 among the network. Okay, we'll discuss alpha in detail and this one in detail. And the sensing power is 1000 milliwatts. The reporting power energy consumption is 1 millijoule for all secondary users, and then the threshold values for cooperative detection and cooperative false alarm probability are 0.9 and 0.1. Okay, let's go back to this part. What we do is, we know TXT was the transmission time maximization. Okay. We first run this transmission time maximization algorithm to obtain the ideal sensing time. And then what we do is we scale it with some alpha value, which changes between 1.1 and 3 to obtain the sensing duration. And then we run the other algorithms. The first one, the optimal one, which what we call as EE, energy efficiency, and then the heuristics. And remember, heuristics assign the number of assign the secondary users greedily to the channels. Okay. As you can see, the loop goes from 1 to m, but actually the number of channels that are picked affect the performance because they are greedy. So we also run the algorithms, the heuristics, with 20 random orderings of the channels. Okay, before we move on to the results, do you have any questions or comments? Yes?
Can we run such algorithm such as water filling or something like that? I mean, we know the received SNRs.
Yes.
And the fusion center or the base center can see the reportings with the SNRs and can assign the weighted, OR algorithm for the channel with highest SNR. For instance, the channel 1 senses the channel and said, yeah, it's free with SNR 10 dB or whatever. And the second channel says, no, it's busy with SNR 7 dB. So the fusion center, based on some kind of water filling, assigns weighted.
Of course, that would be a good modification for the for this type of task. Actually, people do that. Not this kind of complicated, but let's say more simpler scenarios. They already do that. But yes, it would be a good modification actually. Say that if your SNR is higher, I trust you more because you are, let's say, you can achieve more probability of detection. Yeah, that would be a good addition. Discuss methods, and let's start with the energy consumption profiles and transmission time maximization, energy minimization, heuristics, sensing energy minimization, and reporting energy minimization. Now, in this graph, we have two cases. Let's say the first one is SNR with the mean of the exponential is minus 5 decibels, and then high SNR where the mean of the exponential distribution is 2 decibels for SNR values. Now, as I've said before, increasing SNR value decreases energy consumption for all methods. Okay. And since transmission time maximization doesn't care about the energy, it always has the highest energy consumption. And as you can see, the outer linear always has the lowest energy consumption. What's critical is that as the SNR value increases, in case of low SNR, the dominating factor is the energy that is consumed by sensing. Okay, since you have low SNR, you need to have longer sensing durations, and then the sensing energy factor dominates the total energy. On the other hand, when the SNR value increases, the situation just reverses, and then reporting energy becomes the dominating factor because you can achieve satisfactory detection probabilities with little sensing time. You can also observe this from the graphs. As you can see, for low SNR values, this heuristic, which doesn't care about the reporting energy, just looks at the SNR values, achieves a better energy performance than the reporting energy minimization heuristics, while for high SNR, the reporting energy minimization heuristic is superior. Okay, this is a more general graph for changing SNR values, and then we have also the energy on the y-axis, and then you can see increasing SNR value decreases the energy consumption. However, a critical point is that the marginal gain for 1 dB increase decreases as SNR increases. Okay, the marginal gain decreases, and this is just a zoomed in version for this graph between -2 and 3. Okay, just zoomed in version. And now you can say that as a SNR value increases, all methods have lower energy profiles, lower energy consumption. And then if you zoom into this place, as SNR value increases, they also decrease, but the relative gain using the energy efficient method actually increases. And then what we have is, we observe the number of secondary users on the energy consumption. Okay, this one was transmission time maximization, and since it doesn't care about energy, it shows some fluctuations. Okay, but for the other three methods, increasing number of secondary users decreases energy consumption. Why?
Is this total energy consumption?
Yes, but remember, this is the total energy consumption for just a frame. Okay. On the long run, since you have very high number of frames, even a little savings can contribute a lot to the network and then your operating expenses. Okay, we were discussing that increasing the number of secondary users decreases the energy consumption. Why is that? Because more users brings more diversity. Okay. The probability of finding a secondary user with high SNR value increases as there are more secondary users.
So what if you increase the number of sensors a lot? Then the total energy consumption should be increasing, right? Until
No, if you fix the number of channels, okay, this will go something like this, and then it will stay constant after some point, okay? It will not decrease forever.
Okay.
Because let's say that among this 200 secondary users, let's say that you use just, let's say, 60 of them for sensing, okay? If, let's say, you go to this place, about 300, maybe then you will use just, let's say, 50 of them, okay? But it will not increase because you don't utilize all of them. And then remember, alpha was the scaling parameter for the sensing duration, that we scale the ideal sensing duration found by the transmission time maximization by alpha. As you can see, increasing alpha generally means a better performance because you have more sensing time, so you can assign more in an energy conservative manner.
What was the alpha again?
Alpha was the scaling factor that you scale the sensing duration found by this transmission time maximization, and then you use alpha times whatever found by this as your quiet sensing period length. We have just a slight complication here in reporting energy minimization. It does not favor too large quiet sensing period because remember the algorithm favors the secondary users that were already sensing it was prioritizing them. So since it prioritizes them and it has long sensing duration, it makes, how can I say, less worse assignments, okay? Since it prioritizes the reporting secondary users. Now if we conclude this part, in all the graphs we see that for instance, let's say, remember this was the transmission time maximization method, and 1.1 means, let's say this said that 100 milliseconds, let's say, I'm just making this number up, 100 milliseconds is the best sensing period length that you can achieve, and then 1.1 alpha means you use 110 for the other energy minimization methods, okay? And you can see that even a little increase in sensing period length, and increase in sensing period length means decrease in transmission time, can achieve huge energy savings for your network. And by the way, as you can see that we don't have values here for the heuristics, that's because they couldn't come up with a solution. Now, for future work, we can analyze the impact of channel switching, which we already did, and it's the part 2 station, but it's very much shorter. And then different fusion rules, like I've discussed before, and rule, and majority rule, and general counting rule, and maybe some other fusion strategies. And then another future work may be the variable false alarm values. Now we move on to the second part. In this part, we also include the impact of channel switching. And remember, channel switching is tuning your antenna from one frequency to another frequency. And in reality, it is not immediate. In the previous part, we assume that if let's say the secondary user 1 senses channel 1, 3, and 5, the order of these channels is not important, okay? For the previous part. But in reality, tuning to these frequencies incurs an energy and time overhead. So the order becomes an issue. Now in this new case, the frame structure becomes like this. This part is also the same as the previous case, but here you switch to a channel, you have a switching time and switching energy consumption, and then you perform sensing. You switch to another channel, another sensing. Switch, sense, and then after your sensing is done, you just stay idle until the reporting period. And it is assumed that the switching energy from switching from frequency f to f prime is given by this expression where PCS is the switching power and TCS is, let's say, unit switching time or something like that, defined as time required to switch to an adjacent channel. And this is just the absolute value between the separation of these two channels, f and f prime. So if we define Cn to be the ordered set of frequencies that are going to be sensed by n, like f, this is the first frequency to be sensed, second frequency, and so on and so forth, then the switching energy, which is a new component in our energy formulation, becomes this: PCS times TCS, power times unit time, plus this is the initial switch, okay, from the initial channel to the first channel in this set, and then these are the remaining switches. So this is the total switching energy. As an example, consider a secondary user that senses channel 5, 12, 13, and 3. And let's say that its antenna is initially tuned to channel 3. As I've already said before, in the previous case, the order of these channels was not important, but now it is important. So a sensing sequence like this one incurs, let's take a look, 5, 12, 13, 3, and since we begin from 3, 5 minus 3, 2, plus 7, 1, and 10, it becomes 20, right? So 20 times PCS times TCS overhead. But if the sensing sequence was something like this, then it would be 9. Okay, so the order matters here.
Why was it 9?
Because you go from 3 to 3, 0, and then 2, 7, 9, oh, it should be 10. Okay.
And also, don't you, circle like after 13 you will go back to 3 for other frame?
No, this is your sensing sequence for just this frame. So.
Okay, but yeah, all in all, in the long run you have to go back to 3.
But maybe for the next frame, you shouldn't. You won't be sensing these channels. Maybe you will be sensing other channels, because in a dynamic environment, SNR values may change. But of course, that's another case that should be studied. If in a more static environment, if you always sense these channels, then that would be the case actually. Okay, now with channel switching, the definition of the x variable, remember for the previous part we have xmn, and that was equal to 1 if secondary user n senses channel m. Now we have xm, m prime, n, and k. Okay, what does it mean? If secondary user n switches from frequency m to frequency m prime at step k. Okay, now we model this as a network flow for a secondary user n. So a secondary user n starts from its initial channel f0n. And we have some virtual terminal channel phi, which denotes the end of sensing sequence. Okay, it's a virtual thing, non-existent. So, and k means the step number. At step 0, its sensing sequence may go directly to phi, which means it doesn't sense anything, or it may go from one of these channels. And then from these channels, in the first step, it may also go directly to the phi, which again means end of sensing, or some other channel. And then since it can it can sense at most m channels, m steps, and this is the, let's say, network flow of this task.